welcome to our 5th lecture. In this lecture we will cover, this will be actually in Pwm Ii, that is we basically try to cover specific vector modulation technique for the 2-level inverter. So, why space vector? So, space vector is an advanced computational intensive technique that offers the superior performance for the variable speed drive, and same concept has been already taken for the different kind of fax devices, STATCOM and all those things. So, for this reason whatever we do in V by F control and vector control, that concept is already been used for the fax devices. So, in the fax devices also this PWM, this special kind of PWM technique, which must say the space vector modulation is very important. And what is the advantage of it? This technique has the advantage of taking account of the interaction of the phases, and the neutral load current is isolated from the center of the trap and the DC supply. So, it will eliminate the common mode noises and signals, and space vector can be used to minimize the harmonic, because every instant you can check, because what happened in the PWM, we have actually seen the very crude PWM, that is basically your bipolar PWM, where it has got a very huge content of the harmonics. This is instantaneous voltage and the applied voltage has huge error. Thereafter it has been reduced in case of the unipolar PWM, but in case of this in case of this actually space vector, we keep our discussions for the 2-level inverter will be further reduced, and thus we can expect that further reduction of the harmonic that will be presented at the end of the table. Okay. So, what is the definition of it? Space vector essentially represents is a 3-phase quantities. Let us consider that current or voltage mostly we have represented by the XA, XB and XC, and we can see that actually the X is average is a summation of actually 2/3 of XA, XB and XC with a suffix A, but A is basically e to the power j 2 pi by 3, and thus X can be voltage, current, flux, whatever the electrical current quantity, and that can be represented in this fashion. So, this is basically the X, and this can be any quantities, that is current, flux and voltages. So, essentially the average value of this electrical quantity can be represented by this. So, let us consider our 3 sinusoidal voltages. This is a standard system, and let us consider this is their graphical representation. There are 3 sine wave 120 degree apart, and then let us take in some instantaneous value. Assume that at omega t equal to 108. So, what will be the value for Va at that time? It is basically 0.95 and Vb equal to minus 0.208 and Vc equal to 0.78. But what happens generally, what you do? In case of the PWM, you have either apply plus VDC or minus VDC. So, let us see that how it is different here. So, this is the phase system. We assume that actually the anticlockwise rotation. Thereafter, this is basically the magnitude of the Va, which magnitude is actually 0.95. Thereafter, we shall find that magnitude of Vb, which is minus 0.2, and this is actually magnitude of the Vc, and ultimately this is the resultant of it. This is the average value we will apply. So, instead of actually generating these two voltages, these three voltages, if we can generate this black line, and that will be sufficient to generate that necessary parameter to run the machine or fit into the particular voltage required by the STATCOM or other devices. So, let us see that. For this reason, we have chosen a space vector, and where actually this is axis, I assume that we should actually align one of the axis with alpha and another axis should be with the beta. We shall use actually the concept of alpha beta frame and or the DQ frame, DQ DS and the QS are the stationary frame and the DR and the Q are the rotating frame. So, here actually how this actually voltage rotate. Now, in a stationary frame we will be representing this waveform like this. So, actually VA having this magnitude and VB was minus 2 will be given by this magnitude and Vc will be actually this magnitude again minus. So, how actually we can generate these signals with the help of a voltage source inverter and thus how we can calculate the value. So, let us consider a simple 3-phase 2-level voltage source inverter where this point is the negative of the receivers, this is capital N and this is actually the neutral point of the star. And in most of the cases you will have a common mode voltage. Generally we will have a reference VA, BB, VC that will be fed to the, this is gate driver and that will be fed to by the gate driver to generate the desired voltage and generally it will be a closed loop control. And what we want? VA, VB, VC should follow the reference VA star, VB star and the VC star. So, we know that actually according to the definition of the space vector, this average voltage will be actually 2/3 of the VDC, that is actually the maximum it is available will be 2/3 VA, VB, VC with the multiplication of the prefix that is e to the power j omega t. So, and here you can see that the voltage AN, this voltage, this phase voltage will have VAN plus actually the common mode voltage VNN. Same way we will have actually VBN plus VCN, that all will contain with the common mode voltage. But this common mode voltage in this case will be eliminated in case of the line voltage if you subtract. So, this is the average voltage to be fed and you can see that if you add up also, this is basically this summation gives it 0. For this reason your common mode voltage get eliminated. It is the same concept, it has been used for the essentially in case of the third harmonic injection and here we can also offer actually the NN voltage or the common mode voltage 0 and thus this voltage get eliminated. So, thus we can strictly say that VAN is basically the decelerating voltage and the time that the switch up SA is on or off. Similarly, VBN should be similarly VDC into SB and VAN is basically similarly VCN actually can be like that, where SA, SB, SC can be 0 or 1. Thus, we can write V average is 2/3 of VDC by the combinations of the voltage and others are shifted by 120 degree in this mode. So, we can write V bar equal to 2/3 VDC by SA into SA A into SB into A square into SC. So, let us represent by this trapezoid, by this hexagonal. Since this is the phase A, and let us write when it is get a full voltage, when actually upper switch of the phase A is on, that will be represented by the 1 and others are 0. So, for this reason you get a voltage V 1. Similarly, actually this will be 120 degree apart and this will be V B and this value will be 0 1 0. Similarly, this value will be actually 0 0 1. Thus, it will be minus A, it is 0 1 1 and it will be a minus B 1 0 1. Similarly, this will be minus C 1 1 0. So, these are the 6 voltage vector that will generate all the desired voltage you require to generate by the system. So, we will represent it a different sector, task of the controller to identify sector, then accordingly it will actually inject the required voltage vector to generate the desired output. So, this value is a maximum length is basically 2/3 VDC, and here you can, it is a little geometry. So, this will be 1/3 VDC, and thus we require to calculate the different sample time. Let us take an example. We require to let us consider that receiver's voltage is 100 volt and your TS sampling time is actually 100 millisecond, 100 microsecond. That means actually you are considering a 10 kilohertz system. So, see that with the sampling period, VREP is synthesized using the adjacent 0 vector. We will see that how it is synthesized. So, see that, let us consider that your point is somewhere here and you are in a first quadrant. So, this angle alpha will be given to you and the particular magnitude, and you require to understand, or you require to know what, for how much time within the time t actually V 1 voltage to be applied, and rest of the time this actually V 2 voltage to be applied, and thus you will find it out, and whatever the time will left out, we shall apply the null voltage. So, you can go back, there are actually 6 states and there are another 2 states, that is 1 1 1 and 0 0 0. This means SA, SB, SC all are connected to the upper pole, and this means 0 0 0 all are connected to the lower pole. These are 2 are called the null vector. So, in this condition what will happen, the time, let us say it is VT1 and corresponding time will be VT2 and rest of the time will be fed to it by actually the null vector timing, which is be given at the beginning and the end of the cycle. And there is a reason behind it and we will discuss in the subsequent time. Let us consider that this is sector 1. Okay. And let us see the geometry. So, ultimately you can draw a parallel line of V2. So, ultimately for this much of time you require to give V1 and for some amount of time you require to give V2 to generate this desired voltage. So, T1 is applied for the time period T1, V1 is applied, same actually T2 is applied for the time period of V2 and 0 is applied rest of the timing. So, let us see what happened, where VREP is the sample and how this actually 3 phase voltage has been applied. Generally, we start with 0 0 0. Then for the period T1 we apply V1, that this is the time basically the T1, and you apply V1, and thus actually the upper switch of the phase A will be on, essentially it is 1, and this is 0 and this is 0. After this time T1, then you have to apply the voltage VB, and what is this bit combination of VB? That is 1 1 0. So, it is 1 1 0. So, rest of the time, so you have get the desired voltage, but you are left with some time, you have to fill the cavity, and we want 1 bit change. For this reason we apply 1 1 1. We generally what we do, actually we say this time as T7 and we say this time as T0. It should be splitted, half of it at the end and the beginning of the cycle. We want actually less switching. For this reason we shall carry out, so see that actually the whatever has been discussed has been written. Now, let us come to the next sample. So, its past state was, because here there is no history, since its past state was 1 1 1 and you have to apply the null voltage, let us apply the same null voltage to reduce the number of switching. So, for the period again it will be applied 1 1 1. Thereafter, we want 1 bit change, it is 1 1 1, then we should first go to 1 1 0. So, this is actually 1 1 0. Thereafter, we shall go for again 1 0 0 and we shall go to 1 1 1, it 0 0 0. If we interchange it, then what will happen? First of all, it will be a 2 bit change and there will be unnecessary actually the state jump. So, what happened? There will be transition loss will increase. Let us say it was 1 1 1, if I come to 1 0 0, then there is a 2 bit change, that means it will go low. Again here it will go high. So, there will be a unnecessary state change of the switches and thus it will incorporate more switching loss. So, 1 bit change actually ensure there is a less switching state and thus reduce switching losses, and also implementation of this controller will be easy, because you know that it can be implemented by the asynchronous controllers, and if it is an asynchronous controller, if there is a 2 bit change, there can be hazards and other problems which can be avoided by ensuring 1 bit change. Now, the questions becomes how to calculate this timing. So, how much time T1 should be applied, how much time T2 should be applied, and how much time T0 and T7 should be applied. So, let us equate the fault area graph under time t. So, Vref, it will be integrated 0 to t, and that should be equal to actually V0 into dt, that where actually you apply the null voltage. Here you apply V1 for the time t1 and thereafter V2 time t2, thereafter again V7 time 0. So, these two terms are essentially 0 because you have applied the null voltage, they are non-contributory. So, that is the thing. So, ultimately you come with these equations, then just simplification of it, and thus So, Vt can be written as 2/3 Vt into T1 plus 2/3 Vt into cos 30 plus sin 30 into T2. So, we require two equations to solve this. So, another equation is essentially T1 plus T2 plus the null vector timing, that you can write 2 T0 or 2 T7. So, let us assume that angle between them are alpha. So, Vref equal to essentially mod Vrf cos alpha minus j sin alpha. So, from there we can see that actually T into Vref into cos alpha. So, let us equate the voltage across the x plane. Okay. So, from there we can write actually V reference to cos alpha should be 2/3 into Vt into T1 plus 1/3 Vt into T2. Similarly, since there is no component for V1 in y axis, so y axis it should be actually V reference into sin alpha, it will be 1/3 Vt into T2. So, now we can equate, thus we can calculate straight away T1 equal to 2/3, where M is basically this it is an effectively modulation index of the system, that is V reference by Vt by root 3. So, generally what happen in case of the sine triangle PWM, it is we call them actually Vc, V control by V triangle. Here actually it is V reference by Vt, but what essentially you get actually it is 3 times more than this actually the actual modulating index. So, this is one of the advantage, you can use your decelerating voltage better than this actually normal sine triangle PWM. So, this is the value of T1 and this is the value of T2. So, student will be asked to calculate, there will be different time will be given and students are required to calculate what are the timing of T1, T2. So, let us compare sine triangle PWM or combination of SVM with SPVM. So, you can have, this is actually the PWM waveform. For modulation index 1 and for the half bridge configuration, fundamental voltage is VAO for VDC by 2 and line to line voltage will be root 3 by 2 VDC, as simple as that. So, and in case of the SPWM, what you will get? And here you will get that maximum voltage, you are lying with this actually the circle. So, you get 1/3 VDC, and we know that is the maximum possible voltage without over modulation. So, here line to line voltage is VDC and thus in a straighter way we can see that line to line voltage here it is been actually increased by 15%. We almost expect the same kind of increase in case of the third harmonics injection. So, same thing can be achieved by space vector space vector modulation. It gives actually 15% more usage of the decelerating voltage, and moreover it can instantaneously inject the voltage very closer to it. One of the problem of PWM is that you are here and when you are 0 you are applying this voltage, but here this duration is shortened. You just apply for that, when you are applying null vector then only this condition arises, but most of the cases you are switching between one voltage to another voltage, thus you are applying very close voltages and thus actually harmonic content in this SPWM will be much lower than the actually unipolar PWM. Now we shall discuss about selective harmonic elimination. First of all, we take out the selective harmonic eliminations by the help of the sine triangle PWM. So, what happen, we can, if we have this kind of voltages that is available by the PWM, why can't eliminate the unnecessary harmonics? That will be a great help for active filter as well as for the drives application. We know that actually cogging all those issues in the drives. So, fifth harmonic and the seventh harmonic actually gives a pulsating torque. Reduction of this actually those harmonics, which generally it contains actually 6n plus minus harmonic into the system. Reduction of this higher order actually lower order high amplitude harmonic will have its own merit to get better THD, and this can be achieved by this actually selective harmonic elimination. So, how we do that? By placing a notch in the output waveform at a proper location, certain harmonic can be eliminated. It is just like playing a guitar, you touch some point of time, it will form a note here, then that particular harmonic will be eliminated and a multiple of it. This allows lower switching frequency to be used and lower losses, and thus we can use instead of costly IGBTs we can use maybe GTO, and we can actually eliminate those harmonics and we can get the required THD as desired. So, what essentially there is a calculations. So, we require to do the Fourier series analysis. Let us assume that actually it contains all the harmonics, and thus these are the Fourier coefficients. You have studied long time, so no point of any repetition is required. So, ultimately we require to make a particular voltage for the quarter wave symmetry, and we shall ensure that actually only odd harmonic are present, even harmonic are absent. So, ultimately you are left with this actually the Bn. So, within Bn we require to actually calculate, and we can eliminate by choosing the value of the k, we can eliminate different value of the alpha. So, we can by choosing a particular value, let us say k equal to 1. So, you can choose the particular value of alpha. So, that particular frequency can be eliminated. So, you will have that number of notches. If you have 1 notches, you can eliminate one particular frequency. If you have 2 notches, you can eliminate 2 particular frequencies, 5th and 7th. If you have multiple notches, you can eliminate multiple frequencies. And with k alpha angle and k1 harmonics can be eliminated. So, this is the calculations, and this can not be required to compute online, and you can feed, because in space vector modulation mostly it is dynamics, you require to feed this in online. So, let us say we require to try to actually eliminate fundamental should be preserved. So, that will be the B1. So, that value will be given by 1 minus 2 cos alpha plus 2 cos alpha minus 2 cos 3 alpha, and thereafter this to sum will be 0. We require to solve the simultaneous equation and find it out the difference value of alpha 1, alpha 2 and alpha 3, and thus we can eliminate, we can maximize fundamental and we can eliminate 5th and 7th harmonic. So, by calculation we can find it out, alpha 1 required to be 21 degree almost, and alpha 2 equal to 35 degree and alpha 3 equal to 51.2 degree. So, and we can set this offline, and thus those harmonics will be eliminated. Thank you. We shall continue with our discussions. with hysteresis and the current mode control in our next class.